Swayam Prabha. Digital India. Educated India.
Okay, so yeah, let's get started. So far we have kind of dived deeply into this cake cutting problem, and so the focus has been looking at a divisible good, partitioning or fairly dividing a divisible heterogeneous good. We have seen many results in this context. We have and a good summary was provided at the beginning of the previous lecture. It's as good a time as any to sort of step back and see the landscape of fair division, and in fact sort of tease out the choices we have made, like the specific things we have assumed about the problem, so pinpoint them, and what will that will enable us to actually develop a taxonomy for fair division. It will try to tell us, like, okay, what are the, so in some sense, what are the real world problems that can be addressed by the results we have seen so far, by the sort of this framework of cake cutting, and at the same time it will identify its limitations. It will tell us, okay, what are things that we need to sort of revisit, what are directions that we need to still explore and sort of develop new algorithms and results for. So the first thing that kind of the right at the onset, the choice that we made was that the type of resource that we are fairly partitioning is a cake. It was the line segment. So we always said, okay, it's a divisible resource. So it always had there was sort of meaning and usefulness to saying things like, you get 1/4 of the cake, I'll get 3/4 of the cake. So this is indeed the case. Like, we have looked at a divisible good, a divisible resource. But this is certainly not true in all cases. Here's a very sort of stylized example. Consider like a person who's passing on as an inheritance a piece of art among the children. Like, so the father is like saying, okay, here's a valuable painting, and it's being passed on as inheritance among 3 or more children, or even 2 or more children. Now, this is not a divisible resource. You can't just cut the, like a cake, cut it in half and say, okay, here you go, have at it. It's kind of, it's a bad thing to do. There are even more sort of direct examples. Think of resources like laptops, or like things that you cannot, like a seat in a course, or like the sort of option to attend this summer school. So that's a discrete resource. There are so many seats and you guys got chosen. It couldn't have been shared, say, proportionally among all the applicants, right? So it was, in some sense, each seat here was a sort of indivisible resource. It wasn't a cake. So the other option, and this will sort of motivate the second line of work that will sort of focus on for the rest of today, are indivisible goods. So these are indeed goods that cannot be partitioned. They have to be given as a whole. And the problem here is to find partitions, right? Unlike a cake where you were going after intervals, here the idea is to find subsets of goods and partitioning among people, so that again some natural, some meaningful notion of fairness is satisfied. As before, defining fairness is a mathematical art, which sort of we'll get to, but just to sort of at this point, all I want to say is that there is this complementary direction of work. There's this complementary side of things where we look at indivisible goods, which is in sort of stark contrast to what we have been focusing till now, which is cakes, lands, things that can be partitioned fractionally, assigned fractionally. So this is typically referred to as discrete fair division. And as I said, for the rest of today, this will be our poison of choice. Fine. So another sort of important aspect to note that modulo this very brief discussion about burnt cake, we have been looking at cases where you positively or at least non-negatively value the resource or parts of the resource. But of course, you can look at settings where what you have to divide has a negative value overall. So think of the following scenario, again a stylized example. You have a bunch of chores that need to be done. You're sharing an apartment with many friends. Like someone has to clean it, someone has to clean the dishes, yada yada yada. So these are chores. These are not things where the more you get, the more you'll be happy. Okay, some people do like cleaning dishes, but let's say we are not one of those people. So now you have to partition chores instead of goods. So the valuations are negative. So this is sort of what I'm kind of referring to are like generalizations to different contexts of negatively valued object, negatively valued resources. So that's another sort of take we can look at that also is a complementary side of fair division. So that's another option we can sort of throw in the mix that will change the problem setup, that will give us a different thing to look at. So we have been looking at some like the heterogeneous case where different parts of the cake, different parts of the land were valued differently. It wasn't a uniform object. The resource had there was a sort of inherent underlying meaning to different parts having different value. You can think of settings where that's not the case. Say you have to fairly divide river water fairly among two neighboring states. Okay, there's quality issues, but leaving that aside, water is water, and you only care about how many liters of water you get. So in those are scenarios where what you have are called homogeneous goods. They are equally valued, and all you care about is the quantity of the good or the quantity of the goods that you get. And this is again an important direction of work, which for the purposes of this sort of summer school will not get to. But I certainly do want to mention to you that this is also something that's looked at. So if by chance you run into a problem where this is what you have to divide goods of this nature fairly, then in some sense you are in luck. These are intuitively and mathematically simpler objects to deal with. The sort of buzzword you are looking for here, the solution concept of choice, are what are called competitive equilibria with equal incomes. So the umbrella way of fairly dividing such things is to look at markets and look at this notion, which is called CEEI. I'm just throwing this word out there so that if at any point of time you need to look it up, you can. And using this notion, you can sort of study the fair division of these goods. Again, a very sort of developed literature of work in microeconomics and also algorithmic game theory, something that will not sort of get to in the course of these lectures. So that's sort of the categorization, the taxonomy we can obtain by looking at the type of resource we have. The other option, and again this is the sort of choice we sort of made early on, was what are the types of valuations we can focus on. We have been looking like quite a lot. We have seen some sort of variance in it. Like if one way to look at goods versus chores is to actually say that this is a condition on the valuation you are looking at. So again, this sort of falls, and this is not these are not like disjoint characterizations. So that's one. There are two possibilities of looking at valuations. You can look at valuations that are mixed. So parts of the resource you like, positively value, parts of the resource you don't like. It's a burnt cake, so still there's some good parts. So that's one way to categorize valuation and get different fair division problems. So we have focused in the cake setting pretty much focused on additive valuations, where the idea was, okay, if you get two disjoint pieces, the value of this union is just the sum of those two pieces. Again, something that was natural and a good place to start, at least in terms of understanding things. But there are scenarios where this is not the case. There's settings where your valuations can be subadditive. And again, this is, this entire slide is just for you to have, that at some point you want to sort of revisit and see how little of the iceberg we saw, then should be able to appreciate that. We'll not in particular talk about go much beyond additive valuations, but what subadditive valuations do are like capture settings where there is a plateauing effect, right? Okay, let's look at something you eat. Okay, say I give you one dhokla, very nice, your value goes up, give you two, even better, at some point you will stop, hopefully, right? So these are called subadditive valuations. You can't keep getting additional value at, it has to, beyond a point, the marginal utility, the marginal valuation starts decreasing. So those are called subadditive valuations, where it's not necessary that always that the sum of the union, like 5 dhoklas plus 3 dhoklas, that set, the value is not the same as sum of 8 individual dhoklas. So I had to use this analogy since we are in Gujarat, so that's that. So these are typically things that capture the property of substitutes. Right, so like or diminishing marginal returns. In the discrete case, one form of such valuation functions are what are called submodular functions, so on and so forth. So there's a plateauing effect in some, roughly these are like concave functions, if you will. And there's a completely opposite side. You can look at things which are super additive. The idea is that the value is quite low till you get everything. So say now you actually want to cook a dhokla, so you'll need certain ingredients. But if I don't give you everything, I give you, okay, so I give you the mixture batter, I give you oil, but I say, okay, you know what, no gas cylinder for you. Fine, the value is 0, it just doesn't add up. But as soon as you have all of them, your value shoots up. So this is sort of a convex case where the value actually goes up at the end. It's again not additive, right? Till you have the whole thing, it doesn't complete the picture. So these are valuations that are called super additive, and they model this phenomena of complements. So like if you want to make a cake, you need all the ingredients, so things complement each other, and only then do you have a high enough value. So that's sort of again, this is by no means an exhaustive list, but these are 3 different flavors of valuations you look at, and focusing on each, mixing and matching with the type of resource, you will get different fair division problems. So if nothing else from this discussion, you should realize that fair division is a vast space of work. There are lots of interesting things. And even though it's a classic area of research, the first reference I gave you was from an 8th century BC Greek poem from the Bible as well. This is kind of continuing on to be a productive research area, it's a productive area of to sort of develop new ideas, interesting results. Okay, so that's one. I'll continue on and sort of again make another observation to decide between the flavors of problems. So note that throughout we have been discussing settings where money wasn't involved, right? It was a party, and you don't trade like money between friends, so the cake had to be divided. There's nothing like, okay, I'll compensate by your sort of, you buy some amount of money. That wasn't on the table. You just had values, but there was no concept of a monetary transfer. Now think in contrast, or sort of something that's sort of opposite to it, consider a case where, again, among friends, you are renting an apartment. So the apartment has 4 rooms, and between the 4 of you, you will have to pay rent. This is again a very popular sort of problem in fair division. It's called rent division. But there is a natural notion of money here. There's a total amount of rent that must come between the 4 of you. Furthermore, the rooms of the apartment might not be good. There might be like just a room which is the size of a closet, whereas there might be another room which has the best view of Sabarmati, right? So these are different goods. Note that these resources, these rooms are again indivisible, right? You really want your own room. But at the same time, with these sort of distinct rooms, which are indivisible resources, indivisible goods, you have the concept of money. You have to somehow charge people so that the total rent of the apartment is obtained. So this is a setting where monetary transfers are there, and what you get is something that's sort of in contrast to cake division. So this is also like a dichotomy that you can look at to sort of classify fair division problems, whether there's monetary transfers or not. Sort of something that goes in this vein is to look at subsidies. So the idea is fine. There are cases where for some reason or the other you cannot find an ideal fair division. The question with the idea of subsidies is, can you sort of compensate this unfairness with some amount of money, ideally with a minimal amount of money. So that kind of falls under the privy of this classification, looking at fair division problems. So rent division is something we'll sort of circle back to tomorrow, and so it's a fairly interesting fair division sort of paradigm in and of itself. Fine. Okay. Now, finally, the last sort of dichotomy, or the last sort of point where we can separate out fair division problems is something that's been alluded to in the discussions, which is so if we're doing a fair division exercise assuming that the participants are truthful, i.e. we somehow know the valuations, right? We ran all these algorithms for proportional division, say Selfridge-Conway for like NV-free division between 3 agents, assuming that, okay, people will honestly follow the protocol, they will shout out when they have to shout out, they'll not try to game the system, like they'll not say, oh, you know what, you don't value this, I value this, so let me sort of delay calling things, or let me do something else. So this is what we have been sticking to. Of course, we can look at settings where people know their own valuation, the valuation is private information, and they are strategic as well, right? So in the sense that they are not after harming others, but they are not above misreporting their valuation to get a bigger piece of the cake, if you will. So this sort of separation gives us like truthful agents versus strategic agents, and this is certainly like a core, like studying strategic agents is certainly a core aspect of game theory. Again, there's interesting positive and negative results in this space. Again, in the interest of time, we will not get to talking about strategic agents. Throughout the lecture series, we will focus on this case wherein we are dealing with honest, good, truthful agents, i.e. we are dealing with settings where somehow or the other the valuations, the right valuations are known. So in the context, again, let me just point out something that you can read offline, something that's good to know, and there's something called so this is a fair division method for dividing computational resources. So the idea is, okay, there's a server in the university, and the entire university has to use this to run their latest and greatest deep networks code for deep networks, everyone, big machine learning programs, how do you divide it fairly among the sort of users? So how do you partition these computational resources among users? So this is a sort of very nice result that addresses strategic agents. It kind of develops a method for fair division of computational resources such that it is in the best interest of all the users of the computational resource to honestly report their valuations. It's a very specific model. The valuations are also fairly sort of confined to this particular problem context, to the context of computational resources. So, but still, it's a good place to start reading about strategic behavior in the umbrella of fair division. So it's a nice result, again, sort of technically somewhat interesting, technically quite interesting, and it's worth your time to sort of read it when you get a chance. Okay, and if there's interest, I can like pass on some notes or some like papers on this. Okay, so having said that, having laid out the big, and again this is not exhaustive, but it does cover the major sort of pieces, the major flavors of fair division problems. We will now sort of step back and move away from the divisible setting and jump into discrete fair division, jump into sort of so we'll address now the fair division of fair division of indivisible goods. So stop thinking about cakes, start thinking about discrete objects, cell phone, laptops, things that are discrete, that cannot be fractionally assigned. They have to be partitioned as subsets. Okay. So what's the model? Again, what we have are sort of the protagonists of the whole exercise. I have n agents. So this is the set of agents. I'll use this to refer to these agents and index them. So even before I start, note that there will be a distinct flavor of these problems. While fair division of like divisible goods, in particular cake cutting, the references that we saw were like 61, 84, modulo a few exceptions. These were like at least 5 decades old. Indivisible goods, in particular discrete fair division, is a much more recent phenomena, and the surge of interest here actually comes from the computer science community. A lot of work here is much more recent. I mean, most of it would not be more than 10-15 years old. So it's a much more sort of recent thread of work, and furthermore, it has a distinct combinatorial flavor. Right? Instead of talking about topology, Sperner's lemma, and compact sets and closed sequences, I will talk about graphs, acyclic ones, partitions, things that have a more combinatorial flavor, things that will sort of probably make you feel more at ease, more at home. So this entire treatment, again, for one reason or the other, does have a combinatorial flavor, but that's not to say that they are not interesting bridges. A lot of things that will not address, some of the more recent and some of the more involved results actually connect these two strands, and that in and of itself is a nice. So how do you use like topological results, something like Sperner's lemma, to talk about a fair division problem in the indivisible case, in this case of discrete partitioning, discrete objects, discrete items, discrete goods. So that's just sort of the meta level comment I wanted to make before we sort of venture on into this world of indivisible goods. So as before, you have n agents. These agents have distinct preferences. This is what makes the fair division exercise interesting. But instead of a single divisible resource, a single divisible cake, now what you have are m indivisible goods, m indivisible items. And of course, it's interesting to now look at partitioning these goods among these n agents. So no fractional allocations are allowed. You have to, if you pick a good among these m goods, you have to give it to one of the agents, and exactly, or at most one of these agents. So following our nose, we'll continue to define, like specify the preferences of agents through valuation functions. So earlier we had valuations over intervals, but now we'll meaningfully have valuations over subsets of the good. So I pick any subset S of the goods, and now what I have is, so this is my sort of notation that I'll follow throughout our discussion on discrete fair division, is that fine. So what you have is this. So give me any subset of good, this function VA indexed by agent A tells me a value, spits out a number which is the value that this agent A has for a subset of goods S. I'll quickly come to an example, but I do want to sort of, so again, focusing on the case where I don't have negative values for goods, assuming that this value is non-negative. Right? So I give you a subset of goods discretely, these are indivisible goods, and VA will tell you what is the value that agent A has for this subset. So, okay, quick question. I have m indivisible goods. So if I want to say in complete generality, for a specific agent A, I want to specify this function VA. So how many numbers will you have to tell me? Is the question clear? Or, so you have m goods. I fix one agent. I look at the first agent, and I have m indivisible goods. Now I want to specify this function VA, right? I want to, for this specific agent A, I want to tell you what this VA is. So how many values do I really need to spit out or mention? What is that? 2 to the power m, right? I have to tell you this value for in complete generality. I'll have to like tell you this value for every possible subset S. So those are 2 to the power m. So I will again assume normalization that your value for the empty set is 0. But like if I give you nothing, your value is 0. If you get something, the value might be 0 or more. But this is quite a general setup. This is, I mean, even for moderate values of m, it's information overload. So we will sort of kind of more often than not look at a specific class of valuations and as the name suggests, the idea here is that your value for a set of objects is nothing but just a sum of the values that are in this set A. So here so for every good, I now tell you a number This is the value you have for this single indivisible good G. And what you do is define, so now for a, so this is given to you, this values. How many of such values are there? M, right? The M goods, I tell you one number, one value for everything. And now for a subset S, this you just define it to be, you look at all the goods in this set and you sum it up. Hence the name additive. So if I give you three things of value 2, 2 and 4, your value would be 8, 2 plus 2 plus 4. So that's a class of valuations, fairly like a special class, but it's still an important class, useful in many applications, so useful enough to model a lot of settings. So, okay, in contrast to 2 to the m, which is the number of values you had to specify to express a general valuation function, how many values do you need here to specify an additive valuation function in its entirety? What is that? For each agent m, right? So the m values, you can sort of do that. Okay, so here's an example. It will be a running example. So here in this example, I have 3 agents. So n is 3. I'll be doing the fair division exercise among 3 participants. The number of goods is going to be 5. Right? I have 5 goods. And these 5 goods I want to divide fairly among these 3 agents. So the way I'm going to write it is just like a simple matrix, simple table. So what the sort of way to read this table is that if I look at good 1, this good 1 has value 5 for all the 3 agents. Good 2 has value 10 for the first agent, so on. So the way to read it again is like the rows correspond to agents. So for every agent, the number in the particular column tells you the value that this agent has for that specific good. So say I give the third and the fourth good to the second agent, right? So this is an additive valuation case. So I want you to tell me what V2 of G3, G4 is. So note that this is a subset, right? This is some subset S of goods. This is some specific agent. What's the value? What's the answer here? 35. Okay, perfect. Right, so let's keep this example, and what we have done so far is, back to the setup, we have the framework with us, agents, goods, valuations. Now, okay, what's left for us to do is define fairness. And you'll say, look, you have bothered me enough, forcing me to skip India-New Zealand match. Haven't we done this already? Haven't we seen the 2 definitions of fairness, proportionality and envy freeness? And my observation for you is that, okay, we are out of luck if we sort of confine ourselves to these notions in the indivisible world. Right? If I want to achieve envy freeness, that's sort of not necessary to exist. These solution concepts are like, unlike the divisible case where at least proportionality was abound, not just one, we saw two algorithms for it. Now, this is not the case. That's a simple observation. It's an observation that will sort of lead us on our path. Can someone substantiate this for me? Give me an example where this is not the case. Like, I cannot achieve envy freeness. In some sense, this will be the trivialist example you can think of. Someone already said, what's the answer? Yeah, two agents, one good. Right, the father has one valuable painting that's being passed on as an inheritance between two children. So either the first child gets the painting, in which case the second person is envious, or the second one gets it, in which case the first person will be envious. Right, so two agents, one single indivisible good. However, which way you partition it, you will always have envy, and this will not be proportional. You have some value for this single good. Half of it is the proportional value. When you are getting an empty set, your value is 0. Right. So the most trivial case, two agents, one good, you are out of luck. Neither envy freeness nor proportionality is guaranteed to exist, even in this simple case. I mean, you literally didn't have to walk far to find this counterexample. So what we'll do now is look at meaningful relaxations of envy freeness, and later on look at a meaningful relaxation of proportionality. So there will be the analogous solution concept tailored for the indivisible case, and again back to our old exercise, trying to prove existence results, trying to prove efficient algorithms, develop efficient algorithms for these sort of relaxed notions of fairness, for these sort of notions of fairness that have been curated to sort of fit in the indivisible goods case. Okay, so following up on the previous observation, my claim to you is that, okay, even in this example, an envy-free allocation does not exist. So say you had to do it explicitly, right, like completely explicit, like the sort of most naive way of figuring out whether this example has a envy-free solution or not, what would you do? So note that a solution here is something that's a partition of these 5 goods among the 3 agents. My claim to you is that, I mean, there is a particular reason, eyeballing which you can tell me that fine, there will not be a envy-free solution here. What is that? Perfect. Good 5 is the thorn, right? It is it's sort of, in that sense, it's sort of the single good case that has been implanted here. This single good 5 has such a high value for the first 2 agents that, okay, so I have to give this good to one of these 3 agents. In particular, both agent 1 and 2 cannot obtain it. I cannot assign it fractionally. So whoever among these 2 loses this good will be always unhappy, right? The person will always say, look, will certainly be envious. So say agent 1 does not get good 5, even if agent 1 then gets all the remaining 4 goods, the value don't add up to 1000. That's such a large number that the strong sense of dissatisfaction, strong sense of envy sort of pervades. And analogously for agent 2, if you give this good to agent 1 or to agent 3, the second agent, the sum of these values, the value for this the subset of these first 4 goods, for agent 2 will never sort of reach 1500, the large value. So in that sense, you can sort of eyeball again and so note that even in this example, you do not have an envy-free allocation. So So if I look at like the proportional share of these agents, so again this is defined naturally. So this is nothing but the agent looks at the value it has for the entire collection of goods and says, you know what, I'd be happy, I'd consider it a proportionally fair division if I obtain this much. Right. So this is again a threshold based notion of fairness where I would ideally want to achieve this threshold for every agent A. My observation again is that this is not achievable in this example. Why? Again, the reason is this very large values, kind of diamond of a good sitting at the end of things. So the average of say, okay, let's do this thing. So can someone quickly compute in their head the proportional value for agent 1, the proportional share for agent 1? How do you do this? This would be a good question for a class 2 student, so I'm hoping it's a good question here as well. Like modulo the fact that there is some like the notation is a bit, there's some notation, but how do you think addition and division are all that is required? Okay. How do I, let's forget this 1 over n. How do I compute this thing for say the first agent? Yeah, I just sum the row thing. So it's 1000 plus 10 plus 10 plus 10 plus 5. And then to compute this, I divide by 3. Right, it's 3 agents. Note that this is not the average value of the goods, it's the proportional share. It's the proportional value. Proportional in the sense of you're dividing by 3, not by the number of goods. So don't do that mistake. But beyond that, if you sort of go through it, so here for agent 1, the share is equal to 345. Right. So that's sort of the exercise. Again, you can go ahead and sort of convince yourself of the fact that once you lose 1000, like let's say 1000 is not allocated to the first agent, you do not reach 345 by even summing all these goods. So this is also going to hold true for agent 2. Being an indivisible good, one of the two will lose it, and so obviously one of the two will not achieve their proportional share. So again, belabored this point enough. When you are dealing with indivisible goods, NV freeness and proportionality are out the window. You have to sort of think a bit outside the box and keep your fairness notion, like relax it, have a more tractable, more achievable notion in mind. Okay. So that's that. So what we'll now do is kind of look at a definition which relaxes things a bit and gives us a target which we can at least, okay, to begin with, try to aspire towards. So if we go back to the most basic example, 2 agents and 1 good, note that the NV is actually up to 1 good. Right, okay, there is 1 good, but the NV is because there is 1 large valued good that's causing an issue. This is also the case in this example. It's this 1 single large valued good that's causing trouble. Note that here, if there were two large valued goods, we would be slightly in a better position, in the sense that we could say, look, agent 1 gets one of these, agent 2 gets the other one. There might be a way to make them happy. It's that contention towards one single good that's sort of causing trouble. This is very informal, but this kind of leads us to a definition that was defined by Budish. And okay, so before I go on, something that I've been sort of using and hoping that you sort of catch on to is that note that allocations here, divisions here, correspond to subpartitions of the good, right? Like it's not, earlier the division was a collection of intervals, now it's just a collection of subsets. So